Lesson 7, Magnetic Particle Testing, Part 2. Equipment and Materials. The goal of magnetic particle testing is to migrate magnetic particles to a discontinuity so that a highly contrasting indication is visible. The selection of available equipment and materials requires substantial consideration in order to optimize the likelihood of seeing and evaluating indications. The improper selection or use of magnetic particle testing equipment or materials can result in a failure to form indications, the formation of indications too faint for detection, and/or misinterpretation of discontinuities due to distortion or excessive patterns and backgrounds. Stationary magnetic benches. The wet method horizontal magnetic particle test systems typically feature a high current, low voltage output magnetizing source, a head and tail stock to hold the test object and provide electrical contact, a movable coil for longitudinal magnetization, and a particle suspension tank with an agitation system. These basic components, along with magnetizing control indicators and ampere meters, are available in multiple sizes to accommodate most inspection needs. The systems typically provide AC and rectified AC with maximum magnetizing current output from 1 to 10 kiloamps. Of all the equipment available for magnetic particle testing, a stationary bench system is the most versatile in terms of choice in magnetizing current and efficiency of operations. Stationary magnetic particle bench systems are designed to be ergonomic with conveniently positioned control functions. The instrumentation includes liquid crystal displays for digital readouts, or meters in older units, of amperes and smart knobs for fine-tuning of settings. Stationary systems are designed for rugged durability and require minimal practice to operate effectively. Many also have a step-down transformer needed for demagnetization. Bench systems require an array of process controls and maintenance to validate equipment, materials, and processes. Mobile and portable testing units. There are many applications where it is not possible to bring the test object to the stationary magnetic particle system. Mobile and portable units can be transported to the test site and still provide relatively high magnetizing currents. Traditional mobile units can be considered small versions of the power pack systems. Small mobile units have a magnetizing current output of 6 kiloamps, but are limited in size considerations to between 3 and 4 kiloamps. Transportability is also improved by restricting the types of magnetizing current to AC and half-wave. Magnetizing current is applied to the test object by cable wraps, formed coils, prods, and clamps. The term portable equipment refers to compact, lightweight units that can be hand-carried to the test site. Some portable units are mounted on wheeled carts and come in a variety of sizes, shapes, weights, and amperage outputs. The most common method of applying current with a portable unit is with prods or clamps. However, cable wraps and formed coils are also used in many applications. Reduced weight and size are achieved by omitting the step-down transformer needed for demagnetization. Prods. Prods are magnetization accessories that may be used with stationary, power pack, mobile, and portable units. They typically consist of a pair of copper bars 0.5 to 0.75 inches in diameter with handles and connecting cables. One of the prod handles has a trigger to activate the magnetizing current from the unit's mainframe. Prods establish a circular magnetic field that diminishes in intensity as the distance between prods increases. Prods should not be used on components that can be damaged by electrical arcing. Yokes. Yokes can be either alternating current, half-wave alternating current, or both, and are generally powered with conventional AC by a power cable. Some yokes can be powered with a battery. Yokes usually contain a magnetizing coil with a core of laminated transformer iron. Attached to the core are legs that may be either fixed or articulated. When magnetizing current is applied to the coil, a longitudinal magnetic field is created in the core and transmitted to the legs. When in contact with the test specimen, a longitudinal magnetic field is generated between the poles. Demagnetization. A common technique for demagnetizing small objects is to pass them through a coil carrying alternating current. A demagnetization coil is typically a standalone compact bench equipped with an AC rigid copper coil. The AC coil removes residual magnetism of ferromagnetic material after conducting a magnetic particle test. The operation is fairly straightforward with a simple on-off switch to manually pass the magnetized material through the coil. The magnetic field is reduced in amplitude by pulling magnetized material through and away from the coil. Due to the decaying alternating field, the magnetic domains inside the ferromagnetic material return to a random state. The magnetic particles. Magnetic particle testing also requires the proper selection and use of ferromagnetic testing particles in order to obtain the highest quality indication from a particular discontinuity under given conditions. In magnetic particle testing, there are two classes of media, wet and dry. Wet method particles are suspended in a liquid vehicle, water, or light petroleum distillate. Dry method particles are usually applied using a squeeze bulb. Magnetic particles are also classified by the type of pigment bonded to them used to improve visibility. Visible particles are colored to produce a good contrast with the test surface under white or visible light. Fluorescent particles are coated with pigments that fluoresce when exposed to near ultraviolet or UVA light. Dual-use particles are coated with both visible and fluorescent pigments for inspection using visible and UVA light. Dry powders often use iron filings, while wet particles generally use iron oxides. MT particles are highly permeable and easy to magnetize but have low retentivity. Low retentivity is crucial in order to prevent the particles from retaining magnetism. If the particles were to retain magnetism, they would eventually clump together and become useless. The particles can be irregularly shaped, spherical, flakes, or rod-shaped. The properties of different materials, shapes, and types vary widely, but all must have the highest possible permeability to attract the particles at low-level magnetic leakage fields arising from discontinuities. The size and shape of magnetic particles play an important role in how they behave. Generally, sensitivity to very fine discontinuities increases as particle size decreases. However, very small particles may adhere to the surface where there is no leakage field and thus form an objectionable background. Conversely, large, heavy particles are not likely to be attracted and held by a weak leakage field as they move over the object surface. Dry powder particles. A carefully controlled and balanced mixture containing a range of particle sizes provides sensitivity for both fine and large discontinuities without disruptive backgrounds. The smaller particles provide sensitivity and mobility, while larger particles serve a twofold purpose in building up indications at larger discontinuities and reducing background by sweeping finer particles from the test object surface. Wet visible particles. Particles used in a liquid suspension are usually much smaller than those in dry particles. The smaller the discontinuity sought, the smaller the particles should be. Larger particles are difficult to hold in suspension. Wet fluorescent particles. Fluorescent magnetic particles involve bonding pigments around each magnetic particle. This bonding must resist the solvent action of petroleum vehicles and suffocants, as well as the abrasive action stemming from the stationary equipment pump and agitation system. Some manufacturers also encapsulate the bonded dye particles in a layer of resin. As a result of their processing, fluorescent particles have a definite size range that is maintained throughout the suspension service cycle. Dual-use particles are coated with both visible and fluorescent pigments for inspection using visible and UVA light. Visibility and contrast. Visibility and contrast are properties that must be considered when selecting a magnetic particle material for a specific testing application. Choosing a particle color that is easy to see against the test object surface enhances visibility and contrast. Manufacturers bond pigments to iron oxide particles to primarily produce the following colors: white, black, red, blue, and yellow. The color choice depends on the colors of the test object and the test site lighting used. Although fluorescent magnetic particles tend to be magnetically less sensitive than visible particles, they are far superior in terms of visibility and contrast, provided test lighting conditions are ideal. Most specifications require the test site to be darkened to 20 lux or 2-foot candle or less, with a minimum UVA intensity of 1000 microwatts per square centimeter at the test object surface. Proper test site darkening is crucial to gain the benefits of fluorescent particle application. Magnetic particle suspension liquid, also known as the vehicle. MT using stationary bench equipment typically has a reservoir bath of particles suspended in a liquid vehicle. The bath vehicle must have the following: excellent wetting ability to improve surface mobility of magnetic particles across the test specimen surface. Wetting agents are required for water vehicles. anti-foaming agents in water vehicles to circumvent foam due to agitation and wetting agents, corrosion inhibitors in water vehicles to circumvent corrosion of the ferromagnetic test specimens, particles, either fluorescent or visible, suspended with a concentration range of 0.1 to 0.4 milliliters of fluorescent particles, or 1.2 to 2.4 milliliters for color contrast visible particles per 100 milliliter sample in a centrifuge tube. Water-based vehicles are predominantly used in NDT due to the advantages of low cost, low fire hazard, and faster formation of indications. However, oil-based vehicles are used in industry in locations where evaporation is a concern or mandated by standards and specifications. Accessories. In addition to the equipment and materials used for magnetic particle testing, several accessories play an important role in the testing process. Some are used to measure the strength of the magnetic field, some to verify the field direction is correct, and others to measure residual magnetism. The field indicator. The field indicator is a pocket-sized device that measures the relative strength of a field against a set of small enclosed permanent magnets that restricts the needle's movement. The field indicator is used to check if a longitudinal magnetic field exists as a quick reference after magnetization. Also used after performing demagnetization to determine whether the residual field strength has been reduced to a desired level. The pi gauge. A pi gauge is used to verify the direction of a magnetic field. It is placed in the inspection area while the magnetic field is being applied. Pi gauges are available in many configurations and must be qualified to a particular procedure or standard. The device is a disc of high permeability material divided into 4 or more sections by equally spaced cuts that simulate discontinuities. In practice, the indicator is held firmly on a magnetized test object, causing some of the magnetic field to pass through the disc to indicate the direction of the magnetizing force. Gauss/Tesla meter, also known as the Hall effect probe. Gauss or Tesla meters measure the strength of a magnetic field during an inspection. The meter's probe, often called the Hall effect probe, measures the magnetic field as a Gauss or Tesla measurement. The field strength may vary due to polarity, part geometry, and so on. Quantitative quality indicator. A quantitative quality indicator, or QQI, can be used to verify both field direction and field strength. Because of this, and due to its relatively low cost, it is the preferred accessory in many industries for determining the characteristics of a magnetic field. QQIs comprise either .002 or .004 inch thick strips of American Iron and Steel Institute 1005 steel. Specific patterns consist of concentric circles with a plus sign, which are scribed in the material. A QQI can be fitted on most part geometries using clear tape and may be reused if carefully removed after each use. Ultraviolet lamps. Although the entire UV light spectrum is found in the 100 to 400 nanometer wavelength, the longer wavelengths in the 315 to 400 nanometer range, or UVA, are universally used in fluorescent magnetic particle testing. UVA lamps are relatively safe for personnel, come in a variety of shapes and sizes, and react with fluorescent particles best in the 365 nanometer wavelength. Magnetic particle testing process. First, before we get into some of the various testing processes, we need to talk a little bit about safety. As with any industrial occupation, safety is paramount and safety policies must be followed. When performed according to manufacturer and site safety recommendations and requirements, magnetic particle can be safely performed. General safety guidelines include following the written guidance, wearing of personal protective equipment such as goggles and/or face shields, an apron to protect clothes and body, and protective rubber gloves. Remove all jewelry, ensure adequate ventilation, and ensure that the equipment is operating correctly. Additionally, because we're using very strong magnetic forces, individuals with pacemakers are not recommended to be using magnetic particle testing equipment. Sequence of operations. Most parts should already have a specification or a written work directive prepared and approved for use by the Level 3. The written work directive provides specific criteria and test parameters to provide reliable and repeatable test results. Each step decision will affect subsequent steps. Deciding between trade-off and advantage and disadvantages will optimize testing. The sequence of operations consists of 5 steps. Step 1. Evaluate potential discontinuity and material parameters. Step 2. Determine equipment and material availability. Step 3. Determine inspection technique. Step 4. Evaluate and report indications. And Step 5. Demagnetize and post-clean. Step 1. Evaluate potential discontinuity and material parameters. Test material parameters: ferromagnetic, painted, plated, clean, alloy, shape, and condition of part, expected discontinuity location or locations, and material characteristics. The first step in the sequence of operations is critical. It must be determined whether the material or part to be tested is even suitable for magnetic particle testing. Let's discuss a few of the test object considerations. If any of the conditions is considered not acceptable, it must be mitigated or another method of test or inspection must be sought. The ferromagnetic material check. The very first step is to determine whether the material is ferromagnetic. The easiest way to determine this is to use a magnet and see whether it is strongly attracted to the material. If the magnet is not attracted to the material, another test method should be used. Paint and plating. Is the material painted or plated? Thin layers of paint and certain plating substances may be acceptable, however clean bare metal provides the best results. Some codes and specifications require a qualification process to ensure that plating or coating will not adversely affect the test. Cleanliness. Is the material clean enough? Contaminants and corrosion can degrade the magnetic particle bath solution and inspection sensitivity. Alloy, shape, and condition of the part. Will the material composition, geometry, and/or surface conditions impact the testing results? Rougher surfaces can result in particle accumulation, causing false indications, which can cause confusion during the evaluation process. The general rule is that the smoother the surface, the better the evaluation. Expected discontinuity location. What is the history of the part? Is the test object heavy or cumbersome to move? What kinds of discontinuities are suspected, surface or near surface? Is an expected discontinuity orientated in such a way that would create a challenge to magnetize and inspect? Are discontinuities expected on the inner or outer diameter? Answering questions like these will hone in on the best MT technique. Material properties and characteristics. What is the expected permeability and retentivity of the ferromagnetic material? Will it be easy or difficult to magnetize or demagnetize? Step 2. Determine equipment and material availability. Is the equipment to be used stationary, mobile, or portable? What are the particle and vehicle parameters? Are we using fluorescent, visible, wet, or dry? Is there any ancillary equipment that we need, such as field indicators, lighting, and so on? What are the process quality controls? Knowing the portability requirements and what kind of equipment and materials are available and/or can reasonably be attained is a good starting point, and from there the pros and cons of each system component can be weighed. Portable and mobile versus stationary equipment. In general, portable equipment is used for testing when the test object cannot be brought to a stationary bench due to it being too large, too cumbersome, or attached to a larger assembly. Stationary benches are generally considered more efficient in terms of production rate and more versatile in terms of magnetizing current options. Wet suspension or dry particles. In general, wet suspension particles are used with stationary equipment such as wet horizontal units and are preferred for smoother surfaces. These particles are also available in pressurized cans for use with portable equipment. However, the dry particles are most commonly used with AC yokes, DC prods, and permanent magnets. Visible versus fluorescent particles. The most visually sensitive particles are fluorescent. It is always advisable to use dry particles with colors that contrast best with the test surface, but with fluorescent particles, the background is generally black or very dark purple when observing the test under UVA light. Step 3. Determine the inspection technique. What type of current type are we going to be using? AC, half wave, single phase full wave, or three-phase full wave? The magnetizing technique. Are we going to use indirect or direct induction? The magnetism direction. Are we going to be circularly magnetizing the part or longitudinally magnetizing the part? Inspection technique. Are we using the continuous or residual techniques? Continuous versus residual techniques. Magnetic particles can be applied to the test object while the magnetizing force is applied, meaning the continuous technique, or after the magnetizing force is stopped, the residual technique. Unless special circumstances make the residual technique more advantageous, the continuous technique provides greater sensitivity and particle migration to discontinuities. Continuous technique. Continuous magnetization describes the technique where the magnetizing force is applied and maintained while the magnetic particles are dusted for dry particles or flowed for wet particles onto the surface of the component. In a wet horizontal testing unit, the application of the particles is stopped just before the magnetizing force is applied, but since particles are still flowing over the covering of the surface, this is considered continuous magnetization. The continuous technique is generally chosen when maximum sensitivity is required because it has the highest magnetic flux to create the strongest potential flux leakages at discontinuities. Additionally, the continuous technique is advantageous to improve particle mobility. AC or pulse DC will cause the particles to vibrate and move on the surface of the part. This movement allows the particles to travel to leakage sites and create a more visible indication. Overutilization of the continuous technique may create excessive heating in the part, so headshots must be used in moderation. The continuous technique is the only possible method for parts having low retentivity. When using wet particles in the continuous technique, the process is very simple. 1. Flood the test object with particles. 2. Stop the flow of particles and immediately apply current twice in rapid succession to magnetize the part. 3. Allow particles to drain at least 60 seconds. The continuous technique for dry particles. 1. Magnetize the part continuously, meaning that we are keeping the magnetism flowing through the test object while we do 2. Apply the particles during that magnetization. The residual technique. The residual magnetization technique is where the rectified AC magnetizing force is applied to the test specimen and then stopped before applying the magnetic particles. Only the residual field of the magnetized component is used to attract magnetic particles and produce an indication. However, the test object must have a high retentivity to hold the magnetism long enough to attract and build a particle indication over discontinuities. For this reason, objects with a high permeability are not suited for the residual technique. As a rule, the residual technique is most reliable for detection of surface discontinuities and best on automated inspection systems using rectified AC. Care must be exercised when removing the test object from the bath or particle spray. Rapid movement can literally wash off indications held by weak discontinuity leakage fields. The residual technique for wet particles is very simple. 1. We magnetize the part and then stop the current. 2. We apply particles. Then 3. We allow the particles to drain for at least 60 seconds. The residual technique for dry particles is equally simple. 1. We magnetize the part and then stop the current. 2. We apply our particles. Step 4. Evaluate and report indications. After magnetization and particle application comes evaluation. One of the advantages that MT has over some other NDT methods is that discontinuity indications generally resemble the actual discontinuity. Cracks on the surface of the part appear as sharp lines that follow the path of the crack. Discontinuities that exist below the surface of the part are less defined and more difficult to detect. Visible particles. Use a flashlight or natural lighting to gain the best possible contrast advantage to see any particle buildup on the test object surface. Fluorescent particles. Ensure the inspection area is darkened with minimal ambient light leaking in. Optimum darkness is less than 2 foot candles or 20 lux of ambient light. Always allow the eyes to adapt to the darkness for at least 5 minutes. Verify UVA light intensity of at least 1000 microwatts per square centimeter. As we can see from this video here, we can observe the magnetic particle indications as we shine the black light on the area, but because we are in a rather bright area and it is not properly subdued, as soon as the UVA light leaves the area of the MT indications, they disappear. This is why we want to do this fluorescent magnetic particle testing in a very subdued light condition. Indications are any particle accumulation on the surface of the test object. Not all indications are caused by flux leakage fields. Attention must be paid to the size, shape, quantity, grouping, location, and orientation of the indications. Indications must be evaluated collectively to determine their relevance to established criteria. Proficiency in this area comes with experience. ASTM standards and industry specifications are typically used for interpreting indications. Additional criteria to evaluate indications can come from many sources. Typically, the customer, or responsible level 3, will determine the criteria to evaluate indications. After an inspection, technicians are typically required to draft a legible inspection report. The reports are industry or customer specific, but may include the following: specification, procedure, and technique used, equipment type and calibration dates, the inspector's identification, any part information that's available, examination results, indication dimensions, locations of examination area, and photograph or drawing of the discontinuity location and orientation. Any test object that is found to have relevant discontinuities that do not meet the acceptance criteria should be marked with a grease pencil and photographed, marked, and tagged for segregation and reported in detail on the inspection report. Step 5. Demagnetize and post-clean. Material that has been tested using magnetic particle testing retains magnetism. The amount of residual magnetism depends on the material type, hardness, temperature, and condition. Low-carbon steel in the annealed condition, which is the most common, holds only trace amounts of magnetism. However, hardened alloy steels could retain strong magnetic fields for a long period. Typically, demagnetization of the test material is required after MT. Lack of proper demagnetization could create issues with further processing and operations, such as with machining operations due to the attraction of cleaning of metal chips, welding operations due to attraction or repelling of the weld filler metal, causing arc blow, electronic equipment due to the interference of the compasses, digital readouts, and so on, and medical equipment or mechanical equipment, in which cleaning of metal chips may increase internal wear. Demagnetization can be accomplished using a variety of techniques. Reverse electromagnetization subjects a magnetized object to a magnetic force that continually reverses its direction and gradually decreases in intensity. This technique shifts the domains back to the random orientation. A common technique for demagnetizing small objects is to pass them through a coil carrying AC or place the object in a rigid coil or wrapped cables and gradually reducing the current to zero. Many stationary MT units come with a demagnetization feature that slowly reduces the AC in a coil in which the component is placed. Another technique is to use a portable yoke and pull the part and yoke away from one another while applying current. Probably the most effective and universal way to demagnetize material is to heat the material to what's called the Curie temperature. When material is heated above its Curie temperature, it loses its magnetic properties. As a final note on demagnetization, material, especially very long parts, should be demagnetized with the long axis in an east-west orientation to circumvent any influence from the Earth's magnetic field. A field meter is typically used to validate that proper demagnetization is successful by verifying the removal of residual flux. Most specifications and industry standards have a requisite of magnetic flux to be less than 3 Gauss after demagnetization. It is always desirable to demagnetize circularly before longitudinally. As a reminder, circular magnetism cannot be detected with a field meter. Post-cleaning. To post-clean the test object, ensure that all wet inspection bath materials are removed as soon as possible after inspection and demagnetization. Failure to post-clean could lead to abrasive and corrosive conditions on the part. Process quality control. The following discussion will list the most common types of MT process quality control requirements. Regular periodic verification of process control measures is required for accuracy and repeatability in the discovery of expected discontinuities. The only way for an inspector to know for sure if the inspection process is working correctly is to periodically verify performance of the MT equipment and materials. A few common system checks include, but are not limited to, the Quito steel ring check, the water bath quality check, the dead weight test, the ambient and UV light checks, the ammeter check, and the bath particle concentration and contamination check. The Quito steel ring. One of the more commonly known discontinuity standards for magnetic particle testing is a ketose, also known as an AS5282 ring. Each type of ring has holes drilled through it at various thickness depths, with the first hole drilled close to the outside surface and the last hole furthest away. These drilled holes represent discontinuities and are used to verify that a wet MT bench is working properly at various amperage settings and is required by many codes and specifications to validate MT performance. Water bath quality. Wet baths should be carefully controlled to prevent corrosion and provide wettability of testing components. This requires regular chemical analysis of corrosion inhibitor and wetting agent concentration. The dead weight test. This test is used primarily with electromagnetic and permanent magnet yokes to lift steel bars to determine the magnetizing strength. Ambient and UVA light checks. This is the verification of white light and optimum UVA light used in the inspection area. The ammeter check. This check is verification that the ammeter readings coincide with actual amperages flowing into the part or a rigid coil. Bath particle concentration and contamination. It is important that the proportion of magnetic particles in the bath be maintained uniformly after a satisfactory concentration is obtained. If the concentration varies, the strength of the indications will also vary, and interpretation of an indication may be erroneous. Fine indications may be missed entirely with a weak bath. The settling test is intended to measure the concentration of magnetic particles in a suspension. The bath strength for both water and oil bath suspensions should be checked daily before use and after every 8 hours of continuous operation. The recommended range for particle concentration is 0.1 to 0.4 milliliters per 100 milliliters for fluorescent particles and 1.2 to 2.4 milliliters per 100 milliliters for visible particles. When using fluorescent particles, the settling test can also check for background fluorescence. Under UVA light, only the particle layer should fluoresce. Fluorescence in the liquid indicates bath breakdown. Fluorescent pigmentation being stripped from the magnetic particles or fine magnetic particles remaining suspended in media. And that concludes this lesson.